Hello, I'm Chirag, and I will be talking about our paper titled A Characterization of List Learnability. This is a joint work with my advisor, Moses Charikar. One of the simplest machine learning problem settings is that of binary classification. Here, there is an underlying domain X, which we want to label entirely with zeros and ones. Concretely, the learning algorithm is given as input a labeled sample S of size M. The sample consists of xi-yi pairs where the xi's are drawn IID from some unknown distribution D on X. Furthermore, we assume that the labels yi are consistent with some unknown hypothesis H star, which belongs to the known hypothesis class H. This is also known as the realizable setting, and for the purposes of this talk, we will restrict ourselves to this setting. Given S, we want the learning algorithm to predict labels on unseen x's such that they are consistent with the unknown labeling function H star. A standard example for binary classification is that of email spam detection. Here, the input space X comprises of emails, and the binary labels specify whether the email is spam or not spam. Given emails labeled with either spam or not spam as labels, a trained email detector should be able to correctly determine if a new email is spam or not. The mathematical framework that captures this notion of learning was introduced in 1984 in a seminal work by Leslie Valiant. The framework is known as PAC learning, which stands for Probably Approximate Correct Learning. The definition for a hypothesis class H to be PAC learnable is stated here. In words, we say that a hypothesis class H is PAC learnable if there exists a learning algorithm which, when given a finitely large sample of labeled instances drawn from any arbitrary unknown distribution and labeled by any arbitrary unknown target function H star in H, returns a hypothesis which suffers a small error with respect to that distribution. Furthermore, we should be able to obtain this guarantee of small error with high probability over the draw of the labeled instances. The number of samples that must be drawn to obtain this guarantee as a function of the error and the failure probability is termed as the sample complexity. We will think of the error and failure probabilities to be small constants like 0.01 and try to reason about the sample complexity solely as a property of the hypothesis class. So given this definition of PAC learning, a natural question to ask is, when is a binary hypothesis class PAC learnable? More formally, we would like to associate a hypothesis class H with an appropriate complexity parameter that captures its ability to be PAC learned. The fundamental theorem of PAC learning precisely answers this question. Attributed generally to Wapnick and Chervonenkis, the PAC learnability of a binary hypothesis class is governed solely by a simple complexity parameter called the VC dimension of the class. The VC dimension of a hypothesis class is the size of the largest sequence of points that the hypothesis class shatters. By shattering, we want to think of the number of patterns the members of the hypothesis class realize on a sequence of points. We can think of these patterns as 0-1 strings. We say that a sequence of length d is shattered if the hypothesis class realizes all possible 2 to the d binary patterns on the sequence. Then the largest sequence that the class can shatter determines the VC dimension of the class. The PAC learning theorem asserts that the sample complexity of learning a binary hypothesis class is both upper and lower bounded as a linear function of the VC dimension. This means that a hypothesis class with infinite VC dimension in particular cannot be PAC learned. Conversely, it is sufficient for a hypothesis class to have finite VC dimension to ensure PAC learnability. Furthermore, when the VC dimension is finite, the algorithm which simply returns any member of the hypothesis class consistent with the input labeled instances successfully achieves the PAC learning guarantee. This is known as the celebrated empirical risk minimization or ERM principle. The ERM principle is what guides most practical machine learning algorithms towards the task of attaining 100% accuracy on training data. Arguably though, most practical machine learning classification tasks involve more than just 2 labels. That is, we enter the multi-class setting where the number of labels belongs to a discrete set of size L larger than 2. In particular, the number of labels can also be infinite. The setting is still the same, where the learner is provided with a sample drawn from an unknown distribution and labeled according to an unknown function in a class, and we want to correctly label instances it hasn't seen yet. For instance, the input space X can be that of images of animals, and the label space can be the name of the animal. Given the complete characterization of the pack learnability of binary hypothesis classes in terms of the VC dimension, it is natural to ask the same question in the multi-class setting. For the same definition of pack learning, we want to associate every hypothesis class on multiple classes with a single complexity parameter like the VC dimension, such that the parameter completely characterizes pack learnability. Several candidate notions of complexity generalizing the VC dimension have been proposed in the literature towards this. When the number of labels L is finite, two particular notions, known as the Natarajan dimension and the graph dimension, become relevant. These dimensions were introduced in the works of Natarajan and Tadepalli. Each of these complexity parameters defines its own notion of shattering, and again, the size of the largest shattered set is the complexity dimension. In particular, using reductions from the binary setting, it is possible to show that the pack sample complexity is lower bounded by the Natarajan dimension and upper bounded by the graph dimension when the number of labels is finite. Furthermore, the learning algorithm that achieves this upper bound is yet again the ERM principle. A work by Ben David, Cesa Bianchi, Hostler and Long upper bounded the graph dimension in terms of the Natarajan dimension and the number of labels. So this implies that if the number of labels is finite, the Natarajan dimension completely characterizes the pack learnability of the hypothesis class. However, things completely change when the number of labels becomes infinite. In this regime, Natarajan himself constructed a hypothesis class that has infinite graph dimension but is pack learnable by a simple algorithm. This means that finiteness of the graph dimension is not necessary for pack learnability. In fact, already in the multi-class case, some oddities start to show up. Recall that the ERM principle, which returns any hypothesis from the class that is consistent with the training data, is a successful learning algorithm in both the binary and finite labels multi-class case. In 2011, Danieli, Sabato, Ben David and Shalev Schwartz constructed a hypothesis class with Natarajan dimension just 1, where the sample complexities of different ERM rules differ by a factor that is equal to the number of classes. By different ERM rules, we mean two rules that agree with each other on the training data but disagree otherwise. In particular, the infinite labels version of their instance shows an even more interesting phenomenon. Forget the ERM rule. No proper learner at all can learn the class, which we recall has Natarajan dimension just 1. By proper learner, we mean a learning algorithm that is restricted to output a member of the hypothesis class itself. However, they also exhibit an improper learning algorithm which learns the class with only a constant number of samples. So given this curious state of affairs, it was an open question whether the finiteness of the Natarajan dimension guarantees finite pack learning complexity. Note again that we cannot infer this from the stated upper bound here in terms of the Natarajan dimension because it involves a factor of log L, which becomes vacuous when L is infinite. In a breakthrough result last year, Brukim, Karmon, Dinur, Moran and Yehudayov resolved this question in the negative. Concretely, they constructed a hypothesis class on infinite labels that has Natarajan dimension 1 but is not pack learnable. Thus, although finite Natarajan dimension is necessary for learnability, it is not sufficient. In addition, using a beautiful assortment of powerful techniques, they bounded above the sample complexity of pack learning any class with potentially even infinite labels in terms of a complexity parameter called the DS dimension or the Danieli-Shalev-Schwartz dimension. The DS dimension was introduced earlier by Danieli and Shalev-Schwartz in 2014, who showed that the DS dimension also lower bounds the pack sample complexity of learning. However, they left open the question of determining whether the finiteness of this dimension lent itself to a pack learning algorithm. The result by Brukim et al. Settled this question, And we now have a complete characterization of multi-class learnability in terms of the DS dimension. We remark that their learning algorithm, however, is improper, as it must be from the results in the previous slides. We now define the DS dimension, which again is based on its own notion of shattering. Given a sequence S of size D, let us think of the restriction of the class H on S, or the patterns that it realizes on S, as strings of length D on the alphabet 1 through L. Here is an example of a sequence of size 7 on 5 labels. Now, for any index in 1 through D, we say that two functions f and g, to be thought of as strings of length D, are I neighbors at index I if they agree at all indices other than I. Here is an example of f and g that are neighbors at index 5 because they are the same everywhere else other than at index 5. Then, we say that the hypothesis class H DS shatters a sequence S if we can find a finite proper subset script f of H such that every member f in the restriction of script f on S has I neighbors in all directions. And finally, the DS dimension of H is the size of the largest sequence that it can DS shatter. To illustrate better the definition of the DS dimension, let us try to DS shatter a set of size 2. We first think of what this means when the number of labels is just 2. In this case, if we demand members of the restricted class to have neighbors in all directions, but the only available degrees of freedom are 0 and 1, it must be the case that the class realizes all binary patterns on the sequence. That is, DS shattering reduces to VC shattering in the binary case. However, when the number of labels is larger than 2, we start to see different geometric ways to DS shatter this set. Consider this example from Brukim et al., where the number of labels is 6. We can see that each pattern has a neighbor in each of the 2 coordinates, and thus this is a valid DS shattering. Note that the number of patterns realizing this shattering is 6, as opposed to 4 in the binary case. Given that the DS dimension completely characterizes learnability in the multi-class setting, what does one do when the DS dimension is infinite? So naturally, standard pack learning where one seeks to label each point in the domain with a single label goes out of the picture. However, the hypothesis class can admit some additional structure which we can hope to leverage and still learn the class, albeit in a weaker way. This is the key problem that we try to address in our work via the framework of list pack learning. The notion of list learning was also introduced in the work of Brukim et al. In fact, it serves as a crucial building block in their multi-class pack learning algorithm, which involves coming up with a weak list learner. The setting is as it was in the multi-class learning case. We once again have a known hypothesis class on L labels on an input space X. The learner is given a sample labeled by some unknown hypothesis in the class and wants to make accurate predictions on unseen points. However, they have a slightly easier task now. Instead of outputting just one label on an unseen X, they can output a short list of labels instead. The guarantee demanded of them is that the true label on X, according to H star, lies in the list that they predict. For instance, we can once again consider the input space to be the space of animals, images of animals, and the label space to be names of animals. The learner is first given a labeled set of images. They are then presented with a new unseen image. However, we can imagine that this is a particularly confusing image. For instance, it can sometimes get really difficult to differentiate between leopards and jaguars. In such cases, we can ask something less stringent from the learner. They may output a short list containing leopard, jaguar, and cheetah, and we give them full points if the correct answer happens to be any one of these. Note again that the underlying hypothesis class here is still that of normal hypotheses and not list hypotheses, and that the training examples are labeled by a single label. And naturally, if we can learn a class in the standard multi-class setting, we don't need to use the list learning superpower at all. It is only in the case where multi-class learning is not possible that the list learning relaxation becomes relevant. We can think of many cases in practice where this relaxation is useful. As a concrete example, the task of recommender systems on shopping websites is naturally modeled as recommending a list of items to a person, such that the item that they want to buy is contained in the list with good chance. Now for a given list size k, we can define what it means to k-list learn the class in the probably approximately correct framework. The definition is almost identical to the multi-class pack learning definition, and we have highlighted the changes in red. The learner now needs to return a list hypothesis which maps each point in the domain to a list of size k. We say that the learner errs on a point if the true label of the point does not lie in the list predicted by the learner. Note that the list size k is pre-specified for the learning task, and in particular cannot depend on the error and failure probability parameters epsilon and delta. Given this definition, we seek a suitable complexity parameter of the hypothesis class that completely characterizes list learnability of the class for the given list size k. Our main result is to provide such a complete characterization. We show that a suitable generalization of the DS dimension, which we call the KDS dimension, completely characterizes list learnability for a given list size k. That is, we show that the KDS dimension lower bounds the sample complexity of k-list learning, implying that it needs to be finite for list learnability. In addition, we are also able to generalize the techniques of Brukim et al. In a pointwise manner to derive an upper bound on the sample complexity, which is a polynomial function in the list size k, and has the same dependence on the KDS dimension as their result had on the DS dimension. As a bonus, our result improves upon their sample complexity bound of DS to the 1.5 in the case where one happens to know some additional structure about the hypothesis class. Namely, if for some k, the factor k to the 6 times KDS to the 1.5 happens to be much smaller than DS to the 1.5, one can plug in the list learner from our analysis to obtain a better sample complexity. Now recall the definition of the DS dimension. For every member f in the restriction of the function class on a sequence, we required f to have at least a single neighbor in every direction. This suggests a natural extension to the setting of list learning. Namely, for KDS shattering, instead of requiring at least a single neighbor in every direction, we require at least k neighbors in every direction. And that is all. The largest sequence shattered in this way determines the KDS dimension. Here we have highlighted in red the ways in which the KDS dimension differs from the DS dimension. In our example from the previous slide, if k were 2, observe that f has two neighbors g and h in the direction of index 5. Both g and h agree with f at all other indices, but disagree with f on index 5. Thus, f, g, and h are all 5 neighbors, and the green edge connecting them is now actually a hyperedge. Now recall our earlier example where we were DS shattering a set of 2 points with 6 labels. However, observe that this sequence is not 2 DS shattered. This is because every function only has a single neighbor in each direction. For example, we have 1, 2 and 1, 6, but no other function which labels the first point as 1 and the second point as something other than 2 or 6. In order to 2DS shatter the sequence, the hypothesis class has to realize a few additional patterns. Namely, if we add the patterns phi2, 3, 6 and 1, 4, we satisfy the required property of 2DS shattering. Observe that each hypothesis now has 2 neighbors in each of the 2 directions. Each hyperedge is now adjacent to 3 hypotheses and specifies the direction or index at which they differ. To put the definition of the KDS dimension in some more context, we present an example of a simple hypothesis class that has infinite DS dimension, but only a finite KDS dimension, for k equals 2. Here, both the input domain and the label space are the set of natural numbers, and we will think of the hypotheses as infinite strings. The hypothesis class is constructed in a tier-wise manner as a disjoint union of Cartesian products. To start, we have the label set 1, 2, 3 on x equals 1 and 2, whereas on the rest of the natural numbers from 3 to infinity, we have the labels 1, 2. We now take a Cartesian product of these sets. That is, we will include all strings where on the first 2 coordinates, we can have any of 3 labels, whereas on the rest, we will only have 2 labels. We then concatenate this set of strings with another Cartesian product on the next slice of natural numbers. That is, we consider the set of labels 4, 5, 6 on 1 and 2, and only the labels 3 and 4 on the rest of the numbers. We add all these strings to our set. We can keep doing this process, and at each step, we add the Cartesian product of 3 distinct labels on 1, 2 with 2 distinct labels on the rest of the numbers to our set. For the hypotheses class thus constructed, observe that the DS dimension is infinite. In particular, for any finite sequence of size D, we can realize all possible patterns of the labels 1 and 2 on this sequence. Thus, this class is not multi-class pack learnable. Now let us think of its KDS dimension for k equals 2. We can see that the sequence 1, 2 is 2DS shattered because we can realize all patterns with labels 1, 2, 3 on the sequence. However, any sequence of distinct points having size larger than 2 must necessarily contain an index which is larger than 2, and such a sequence cannot be 2DS shattered. Namely, for any fixed labeling of all points in the sequence, we can only realize 2 different labels on this index. This is an artifact of the tier-wise manner in which we constructed the class, where we didn't mix the labels in each tier. Thus, the 2DS dimension of this class is just 2, and our theorem now implies that this class can be list pack learned with list size 2, even though it cannot be pack learned in the standard multi-class setting. We will now try to motivate why the KDS dimension shows up as the main complexity parameter in our theorem. To do this, we will have to first describe an important combinatorial object associated with a hypothesis class known as the one-inclusion graph. The one-inclusion graph of a hypothesis class on the integers 1 through m is actually a hypergraph. Each hypothesis in the class is a vertex in the hypergraph. Each edge can be thought of as a labeling to all but one of the m indices. The unlabeled index is the direction of the edge, and the vertices adjacent to the edge are precisely all the hypotheses that complete the labeling on the missing index while being consistent with the labeling specified by the edge. Observe that every hypothesis is adjacent to exactly m edges. We have one edge for each of the m coordinates that we hide. To illustrate, here is our example hypothesis class on 2 points from a couple slides ago. We have 9 hypotheses in this class, each of which is a vertex in the one-inclusion graph. The green hyperedges represent neighbors in the direction of the first coordinate. That is, each green hyperedge connects hypotheses that vary in the first coordinate but have a fixed label on the second coordinate. Similarly, each blue hyperedge connects hypotheses that vary in the second coordinate but have a fixed label on the first coordinate. We can now define a learning game over the one-inclusion graph of a hypothesis class called the transductive learning game. In this game, nature first picks a vertex from the one-inclusion graph from some unknown distribution. Then it selects an edge adjacent to this vertex uniformly at random and hands it over to the learner. Recall that the edge represents a labeling to all the points except one. The labeled points can be thought of as the training data presented to the learner, and the unlabeled point can be thought of as the test data point. The learner has to predict a short list of labels for the unlabeled point, and they win if the label they predict is consistent with the vertex that nature had picked at the start. As an example, imagine that nature picked the vertex 5, 6 in this picture. Then say that it picked the blue edge 2, 5 in the direction of the second coordinate and presented it to the learner. That is, the learner is told that the label on the first coordinate is 5 and is asked to make a list prediction on the second coordinate. The learner wins if the list that they predict contains 6, because that is what the vertex 5, 6 labels the second coordinate with. We can see that the KDS dimension precisely captures the difficulty of winning the transductive learning game for a list size k. Intuitively, this happens because the number of vertices that an edge is adjacent to in the one inclusion graph is precisely the number of I neighbors that these vertices have in that direction. More formally, consider playing the transductive learning game on the one inclusion graph of the class restricted to a KDS shattered set, where the initial vertex distribution is also uniform. Conditioned on the learner receiving any fixed edge, the true label on the unlabeled point is a uniformly random label over the vertices adjacent to this edge. But because this set is KDS shattered, there are a total of k plus 1 vertices adjacent to each edge. Because the learner can only output a list of size k, there is a mass of 1 over k plus 1 on the label that the k-list learner misses out, and thus they lose with a probability of at least 1 over k plus 1. In pictures, suppose the learner received the edge 2, 5. That is, they are told that the label on the first coordinate is 5. Now, the label on the second coordinate is uniform over 2, 4, 6, and a list of size 2 definitely misses out on at least a 1/3 mass. We can port over this transductive learning argument over the largest KDS shattered set to the pack learning setting, yielding a list pack learning lower bound of omega KDS. We now turn towards the upper bound. For this, we will have to define the notion of orienting the hyperedges of the one inclusion graph. A list orientation sigma of the one inclusion graph corresponds to mapping every hyperedge to a k-size subset of the vertices it is adjacent to. Every list orientation represents a deterministic list learning algorithm in the transductive learning game. Namely, the output of the learner given an edge is precisely given by the list of vertices it is oriented towards. In our picture, the arrowheads on the edges represent the vertices that the edges are oriented towards, and we think of k equals 2, so each edge points to 2 vertices. Now, say the learner is given the edge 1, 2 as input. Then, since this edge is oriented towards the vertices 1, 2 and 3, 2, the learner outputs the list 1, 3 on the first coordinate. The goodness of a list orientation is given by the out degree of the orientation. Namely, smaller out degree is better. What is the out degree of a vertex in a list orientation? It is simply the number of edges that the vertex is adjacent to that have not been oriented towards it. The out degree of the entire orientation is the largest out degree of all of the vertices in the graph. The out degree of a vertex determines the probability that the learner wins if they were presented with an edge adjacent to this vertex. For example, say we consider the list orientation as given in the picture. Since every edge adjacent to the vertex 1, 2 is oriented towards it, if nature had picked any edge adjacent to this vertex, the learner wins regardless. On the other hand, observe that none of the edges that the vertex phi 2 is adjacent to points towards it. Thus, if nature had chosen an edge adjacent to this vertex to give to the learner, they would definitely lose. Moreover, since the initial distribution is arbitrary, the distribution can have all of its mass on the vertex with the largest out degree. Thus, the out degree of the worst vertex determines the success probability of the learner. Given this, the main insight behind the upper bound is that one inclusion graphs of hypothesis classes having bounded KDS degree allow constructing list orientations having a small out degree. More formally, consider a hypothesis class on d plus 1 points having KDS dimension at most d. Then, we can orient the edges of its one inclusion graph in such a way that the worst out degree is at most d. The proof of this is by induction on the size of the class. For the base case, we have only one hypothesis in the class, and we simply orient all the edges it is adjacent to towards it, achieving out degree 0. Now, say the hypothesis class has size larger than 1. Since the KDS dimension of the class is at most d, there must exist a member h that is adjacent to an edge of size at most k. If this is not the case, every hypothesis has at least k neighbors in all d plus 1 directions, which would mean that the KDS dimension is d plus 1. We find this hypothesis, h, and remove it from the class to obtain h prime, having size 1 less than h. By the inductive hypothesis, H prime has a list orientation sigma tilde of outdegree at most D. Now we add H back to H prime and obtain the required list orientation with outdegree at most D in the following way. We find the edge that has size at most k after adding H, which as we argued has to exist. This edge could only have been adjacent to k-1 hypotheses in H prime since we had removed H, and thus it could only have been oriented towards k-1 hypotheses. We now additionally orient this edge towards H in the new list orientation sigma. For all other edges, we keep their orientations as it was. Note that this new orientation does not affect the outdegree of any hypotheses other than the one we removed, and so by the inductive hypotheses, all those have outdegree at most D. Furthermore, since we oriented at least one edge towards H, H's outdegree is also at most D, completing the proof. With this insight, we can readily obtain a list learner for the transductive learning game that enjoys a small constant probability of success. The algorithm is popularly known in the theory community as the one inclusion graph algorithm. Recall that the learner's input is an edge from the one inclusion graph of a hypothesis class on D+1 points with KDS dimension at most D. The learner constructs the one inclusion graph of edge and finds a list orientation that minimizes the maximum outdegree of any vertex. By the lemma on the previous slide, this orientation has outdegree at most D. They then find the edge that they have been presented with as input and look at the list of k vertices it is oriented towards. Each of these hypotheses assigns a particular label to the test point, and the learner collects these labels and outputs them as a list. As we argued, since every vertex has at least one of the D+1 edges it is adjacent to oriented towards it, this learner wins the transductive learning game with probability at least 1 over D+1. This weak learner is a starting point of the list learning algorithm from our upper bound in our result. To conclude, we consider learning tasks where standard multi-class packed learning is not possible. In this setting, we instead consider learning short lists. We provide a complete characterization of this task for every fixed list size k via a complexity parameter which we call the KDS dimension. The KDS dimension is a natural generalization of the DS dimension to the list learning task. We saw in the previous slides how a bound on the KDS dimension allows us to construct list orientations of the one inclusion graph that have small outdegree. This in turn guarantees a small probability of success. In order to derive our final upper bound in the pack learning model, we generalize the heavy machinery built by Brukim et al., which involves shifting, sample compression, etc., as well as a few other tools like a list variant of Sauer's lemma. We also show that it is necessary for the KDS dimension to be finite for list learnability to be possible. As we can see though, there is a considerable gap in the lower bound and the upper bound. The KDS versus KDS to the 1.5 gap is a direct consequence of the same gap existing in Brukim et al.'s result, and it would be interesting to close this gap even in the standard multi-class setting. As more ambitious directions, it would be nice if there was some way to assign weights to the list of vertices that an edge is oriented to in the one inclusion graph. Then, it may be conceivable to take a weighted combination of the hypotheses that an edge is oriented towards, where the weights may be obtained in a similar fashion as boosting. This can potentially lead to list learning algorithms with stronger guarantees or even better multi-class learning algorithms. Finally, given the extent to which list decoding has empowered the field of coding theory, it is natural to wonder if there are any insights which can be drawn from there that can be ported over to list pack learning. Thank you for listening.